Right, good afternoon, ladies and gentlemen. Today we are going to start the section 2.5 numerical calculation and estimation. So the section 2.5a, there are three terms. They are scientific notation, which is 科学符号, significant figures is 有效数字, and precision is 准确度. So let's start from the scientific notation. You know, if you want to describe a very big number or very small number, for example, like 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, this number, how can you do it in a smart way? Yes, this is the reason we want to use scientific notation. You can describe this number using 1.23 times 10 to 15th. So you can use this number is between 0.1 to 10. Normally we use 1 to 10 or something. And this is 10 to something, a number. Or you can write down like this 0.123 times 10 to 16th. Both ways are okay, but normally we use this. How about a very small number like 0.000028? You can write down as a 2.8 times 10 to minus 5. Though this number looks smarter than this number, right? Or this number is smarter than this number. Okay? So this is what we call scientific notation. How about significant figures? Let's imagine using a balance as an example. A balance is like this. For example, if you have 1.23 grams, that means if you put a sample into the balance and the number show you is 1.23, right? Is the maximum, this is 50, right? 50.00. That means there are two numbers after the decimal point. Okay, so this is how do you describe this? This is significant. Or if you have a balance which has a 1, 2, 3, 4, 5, 6, you have 6 digital numbers after decimal point. So you might write down like this: 1.230000 grams. Because you use the same sample, right? So they will give you the same answer normally. So however, this balance only give you 2 digital numbers after decimal point. This balance give you 6 digital numbers after decimal points. So how are you going to describe these two? We use significant figures to describe, wow, this is more precision than this number. So the significant figures is that if this number has a decimal point, then how do you count the significant figure? From the first non-zero digit on the left, and then count to the zero or non-zero numbers on the right, from left to the right. Here I give you an example. From left to the right, if this has a decimal point, this number has a decimal point, right? So you count from the very last non-zero, first non-zero digital on the left, which is 3, and count to the right, 0 or non-zero. So this is 0 or non-zero, right? So here 1, 2, 3. So you have 3 significant figures. And how about this? You count 1, 2, right? You have 2 significant figures. That means what? This has 3 significant figures, although you see the same numbers, right? So they have 3 significant figures. This is 2 significant figures. If you think of using balance, this balance is better than this balance, right? So because this balance has 1, 2, 3, 4, 5 digital numbers after decimal point. This has a 1, 2, 3, 4 digital number after decimal point. And the significant figure for this number is 3. The significant figures for this number is 2. Okay, how about this one? 50.00. So you count from the first 5, 1, 2, 3. You have decimal number, right? Decimal number points. So you count from left 1, 2, 3, 4. There are 4-digit number, which is exactly this number. If you have 5, you don't write 50. No, because if you write 50, there are only one digital number, one significant figures. Let me show you. So if there is no decimal point, then you have to count from the left hand side from the non-zero first and until the non-zero. So here is 1, 2, 3, 4. There are 4 digital number, 4 significant figures. And this one, which has 4, 7, 8, 9, 1, 2, right? So there are 6 digital number. So this is a 4 significant figures. So if you compare this balance has only good until 100 grams, right? And this is precision. This balance has a 6 is precision to the 1 gram. Okay. So let me show you more information. How about this one? 2300. That this is how many significant figures here? 2, right? First 1, 2, and you don't count this because there is no decimal point. And how do you write this in scientific notation? 2.3 times 10 to 3, right? So this is 2 significant figures. How about this one? There's a decimal point. So you know that 1, 2, 3, 4. So you need to write significant figures 4. Always use balance to think of these significant figures, right? This balance is good until here. This balance is good until here, this number. How about 2300.0? There are 5 significant figures. Okay? How about this one? There are 4 significant figures. How about this one? There are 2. It's your decimal point, right? Come from the first one to the end. There are 2 significant figures. How about this one? It's count here from decimal point 1, 2, 3, 4. There are 4 significant figures. So this balance is better than this balance, right? Because there are more digital numbers after decimal point. So if you have good higher significant figures, you have a better balance, right? So that's why we call precision. What's the definition of precision? The numbers of the significant figures in this reported value of a measured or calculated quantities provides an indication of precision with which the quantities is known. So let's think of the precision. If you have a sample, you put on the balance here, and 8.3, the significant figures is 2, right? It can be what? Because it can be 8.25 or 8.34. It depends on round-off. How do you do the round-off? Right? How about this? 8.300. So you have precision. You have 4 precisions. 4 significant figures. So this number has a better precision than this number. So it can be 8.2995 or it can be 8.3004. It depends on it, because you run off this, right? You run off these numbers, you can become this. So if you have a higher significant number figures, you will have a better precision. Okay. So now the question is, if I have 1 car or 1 person, What's the significant figures? Because it's 1, right? Exactly 1. So it's a pure integer. So this precision is very, very high. So significant figure is infinite. Can be 0, 0, 0, 0, 0, 0, 0. So this is a precision very, very high. The 1 cow. Okay? The value is non-precisely. Right. So now let's think of how to do the calculation of the significant figures using adding, subtraction, multiplication, and division. Again, let's use balances as an example. If I put a sample here and I got the numbers of 45.31 grams, you know, there are 2 digital numbers at the decimal point, right? So you can get 45.31 grams. Okay, you have another samples. Put it here, which has 1, 2, 3, 4, 5, 6 digital numbers at the decimal point. So you can get numbers something like this. So it's 1.2368711 grams. And you want to put these 2 samples together. So you add up these 2 numbers. The answer you get is 46.54688711 gram. Is this the correct number? No, this is not correct. Why? Because the precision, this number can be 44.308 or 45.312. So if you have used this number to add up this number, this number to add up this number, the number here is meaningless, right? It's meaningless. So how can we do the subtraction, addition, or division with these numbers? There's a rules. So first of all, let's take a look of the addition and subtraction. So the addition and subtraction is that if you need to take a look of the position of the significant figures, and you had to get the highest. So the rule for the additions and subtraction concerns the position of the last significant figures in sum. You might not understand this, but don't worry. I'm going to give you an example. So for example, if you have a number which is 1330 and 1530 minus 2.56, you can regard this as a balance. You got this number from a balance. You got this number from a balance. So location of these figures related to the decimal points. So you have to line up with the decimal point here. Of course, you can do a simple calculation, and you got answers 1527.44. So if you can't purely do the calculation like this is correct answer. But if you consider the precision and significant figures using concept of a balance, so this 1430, this arrow is the one farthest to the left, right? So this is you have 3 significant figures. And you have also 3 significant figures, but this is the one farthest to the left. Okay? And then in the end, you got an answer like this. And how do you do the addition and subtraction with the consideration of the significant figures? So the position of the last significant figures in sum will be this one. So this one, regardless of this arrow, you will have to count this one. So this one, after this number, this 7 should be round off. So the answer you will get is what? Round off will be add 1 here. So 1530. So you might ask me the question, Professor, 1530 minus 2.56, y equal to 1530, which is the same, right? This is pure mathematics. But if you think of the precision using the physical meaning of the significant figures, then you will get this answer. 1530 minus 2.65 equal to 1530. Okay? So here I give you another example. It's 1.0000 plus 0.036 plus 0.22. Of course, if you do the pure mathematics, you got 1.2560. However, if you consider the significant figures and precision, you had to use a law, right? So this is error. Here, significant figures 5. This is what? This is this one, and this is this one. So you need to choose the error most close to the left-hand side. So this is one. So the precision will be here. So the significant figure should be 1, 2, 3. So 1, 2, 3. So it's what? This one. And this one round off. So the answer you will get is 1.26. Okay? How about this one? 2.75 times 10 to 6 plus 3.400 times 10 to 4th. Okay, the key point here is you need to make this power the same. Okay, so let's make it power 6 first. So as a result, you have the 2.75 times 0.03600. So as a result, you have this, you have error here and error here. Sorry, here, right? Because you have decimal point. Sorry, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so in the end, you choose this error, which is closer to the left-hand side. So the answer you will get is 2.784000. And if you count on this, then that will be 2.78 times 10 to 6. Okay? So we finish addition and subtraction. So now let's think of the multiplication and the division. So for the multiplication and division, it's easier. You choose the lowest numbers of the significant figures. Here is an example. So 3.57 times 4.286. Then you have 3 digital significant figures. You have 4. And the answer you will get will be 15.301102. Then you have 3 here, and you have 4 here, and you have 7 here, significant figures. And in the end, you need to choose 3. So 1, 2, 3, and 0 here. So you round off here, so you have 15.3. Okay? How about this one? Significant figures. 2 significant figures. 4 significant figures. 3. So if you do the simple mathematical calculation, you will get 318.4269966. But however, if you need to choose the lowest significant figures, which is 2, so you have 2 here, right? So, and this one round off. So the answer you will get is 320. So you have got significant figures 9, right? So you have got 320. Okay? So this is the answer. Right, let's do more practice. The 4 times 12, it should be 48, right? However, if you count with the significant figures, this 1, this is 2, so in the end, you'll get 50. Because 48, you have got only 1, you have to round off the 8 and go up to 8, 4 plus 1, that will be 5, that will be 50. However, if you want to really write down 48, how can you do that? 4.0 times 12. So there are two significant figures. There are two significant figures. So in the end, you will get two significant figures. How about this one? The 60 point, that means how many significant figures here? 2, right? Because if you don't have decimal point here, you will only have one significant figure. Okay, so this is 2, this is 5 significant figures. And how many significant figures here? 6, right? So because you want to have two significant figures here, so as a result, 303.834, that means in the end you will get, because you will have run of this, so you got 300. But there's something wrong with this number, because you need to get the number with two significant figures. But however, this number only give you one significant figures. So what can we do? This is another important thing for the scientific notation, because you can write down like this. So this one give you the two significant figures. Okay, so instead of writing 3000, you can write down 3.0 times 10 to second. Okay, this is the conclusion of 2.5a. Important thing is you need to remember 3 terms. The first one is called scientific notation, second one is significant figures, and the third one is precision. And you need to know how to do the addition, subtraction, multiplication, and division of the numbers using significant figures. Okay, let's move to the section 2.5b, validating results. You know, every problem, or when you try to solve the problems, the first one is, how can I get a solution, right? You can write, if I give you a problem or you got a question set, if I give you a question, you need to find out how to solve the problems. Okay, you get an answer. In the end, you get an answer. It might be a number, right? And once you got a number for your answer, then you need to know, how can I validate the results? When I get 1, how do I know it's right? The number is right. Okay, solve the problem, you get the answer, and you need to check whether your answer is right or not. Right? So normally there are 3 directions for you to find out. The first direction is we call back substitution. The number you got, and you do the back substitution, and you find out this answer is right or not. But this is time consuming. This is it will take you a lot of time. Another one is order of magnitude estimation. What is order of magnitude estimation? Is that if you got an answer which is 27.36, you use 20 or basically 30 to do the back subtraction. Okay, if you got a number of this, you don't want to do ready calculation like this. You use 60,000 to check whether your answer is right. Okay, so this is save your time and you can do it quicker to estimate, to validate the results. So once you got the answer, the third direction is apply the test of the reasonableness. Okay, reasonableness means what? If you got an answer of the flow rate, and the flow rate is faster than speed of the light, in that case, this is wrong, right? It doesn't make sense. The flow rate of the fluid will be faster than the speed of light, so you know the answer is wrong. Okay. So there are some examples. I don't have time for you. Please practice by yourself. So let's move to the section 2.5c, estimation of the measure values. How do you estimate of the measure values? The first topic we want to introduce you is sample means. Right, this is a question. This is a kind of example. If you have a chemical A, you put into this tank, and the chemical A at 45 Celsius will convert to, for example, products. Let's say chemical B. So material A here under the temperature of 45, and you convert to the product B. And this is an analyzer which takes the conversion rate. Conversion rate means that the percentage of A convert to the product B. This is called conversion rate. Okay, conversion. Okay, so this analyzer take the sample every 2 minutes. Take it. If you start to run the experiment, and after second minutes, you have an analyzer to see the conversion rate here. So you have a temperature meter, we can be thermocouple, right? Or you have a coolant, because chemical reaction can increase the temperature. So you have to do the balance. You have to control the temperature to the 45 Celsius. Okay, so you have control the temperature. This is sensor. This is stirrer to mix the A material to B material and B materials. So the sample tab, you open this tab after reaction of 2 minutes, you got an analyzer, and then you do it 10 times of this experiment, or you ask 10 people to do the same experiment, and you got an answer like this. After 2 seconds, the first person got a conversion rate here is 67.1. The second person is 73.1. Third experiment is 69.1. So it doesn't matter if you do 10 experiments, 10 same experiments, or you ask 10 people to do the experiments. This is the conversion rate. Okay, for 10 times. So if you plot like this is run number 1, number 2, number 3, number 4, number 10. And this is, the first one is 60.1 point here, the conversion rate, y-axis is conversion rate, right? And then the second run is 33.1. This is 69.1, something like this. So there are 10 experiments. And now the question is, why run 1, the conversion rate is different from the run 2, run 3, run 4, run 5. And to be honest, to be exact, there's no conversion rate is the same. Why run 1 to run 10 are different? Why? Give me the answer. It can be temperature variance, right? Because the temperature change all the time, and the coolant try to control the temperature. It can be 45, or it can be 45.1, it can be 45.3, it can be 44.9, because it depends on the precision of this temperature meter, thermometer, right? Okay, so sampling after 2 minutes. So after 2 minutes, you open the tap, and then the fluid will go through this pipe and then goes into the analyzer and give you the data. So 2 minutes, it can be 2.01 minutes or 1.99 minutes. So it can be different. Another thing is analyzer problem. Analyzer problem is that if analyzer is not correct, you need to do the calibration, or you have problems with different analyzer. So what's the true value of the X? Because you run the 10 times experiment, you got all the different answers. So how can we estimate the true value of X? Where is the X most close to the true value? So this is what we want to introduce one terms, which is sample means. So which one is more correct? We don't know, but we can average these 10 points, right? So this is called sample means, which is also arithmetic means. Arithmetic means that x over bar equal to n. N is the number. In this case, it's 10, right? And this is the numbers of the conversion, right? It can be 61, 69, 71, something like this. And this is the number of the rungs, right? Rung numbers. And you parenthesis this together, and you give an equation like this. Okay, so under this estimation, you will understand the average of these 10 rungs will, the conversion will be 69.3%. This is the average. Okay, simple. Okay, so but what is the true value? Is this 69.3 is the true value? No, it's a kind of average only, because nobody knows what is true. Who knows who is the true value? But it might be more close to the 69.3 might be closer to the true value, right? So we can use arithmetic means to represent this data, right? However, if you run 20 times, 100 times, you will get more precise numbers, which is if you run more experiments, the sample means close to the true value. Okay? Right, so now let's move to the 2.5D, sample variance of the scatter data. Okay, now if we have two groups and we got the same arithmetic means, the two groups students got the same arithmetic means. The group A, the data set 1, we got numbers like this, 1, 2, 3, 4, 5, 6, they are 10 rungs. And data set B2 is like this, right? There are 10 rungs. Okay, and again, y-axis is the conversion rate. So which set give you a better estimation? Set A or set B? Set 1 or set 2? Answer is the same, right? Because I'm sorry, I just make a trick, right? Because the Y scale in the very beginning, you need to distinguish which set is better. You need to see the axis first and scale. This scale is from 0 to 100. This scale is from 60 to 79. Actually, these 10 data represent the same data as this. I just made the scale bar bigger. Okay, from 0 to 100. But these 10 data are the same. So actually, the set data A is same as set data B. This is case 1. Okay, let's take a look of the case 2. Right, so we have 10 data here, 10 data here. And then the set data A, data set A, and data set B, which one is better? I'm sure you understand. This is the highest, this one is might go to 90 or something. Lowest go to 50, right? And this one, the highest might be go to 75, and lowest go to 67, for example, right? So this set is better than this set. That's for sure. So, however, these two has all the same arithmetic mean, but you understand this set is better than this set. So once we know, once we tell you that this set is better than this set, this is called qualitative. This is better than this. But how good? How bad? How good is this data? How bad is this data? We need to know. We call it quantitative. We don't know quantitative at this moment. So we need to have a number to tell you how good is this. It's bad. how good is this set better than this set? Okay, this is better than this one. This is called qualitative. And we want to know quantitative. Okay? So how can we do the quantitative analysis? Quantitative analysis is you can use range. You can use sample variance. You can use sample standard deviation. Okay, so let's use this as an example. So first one is range, right? Range is x maximum minus x minimum. So x maximum in this data set will be here. This is x maximum, which is 72%. And x minimum will be this one, which is 68%. So the range will be 72 minus 68%, which is 4%. However, for the data set B, the maximum will be 95%, the minimum will be 52%. So the range will be this number, and which is much higher than this number. So we know this data is better than this data set is better than this data set, and we use quantitative analysis to show you this beta is better than this data. However, is the range the only way to describe the differences? No, this is another example called sample variance. We use s power 2x to represent sample variance. Sample variance is very easy as you learn. I think you might learn this when you are in high school. Standard variance is equal to this. If you have average, right? And this number minus average x over bar power 2 plus this x over bar number x over bar power 2 plus this minus this x over bar plus this minus this over bar power 2, and then divided by n1. N is the number of the run. Okay? So, as you know, if we have a smaller list, you got smaller list. So if the sample variance decrease, the data scattering decrease. So you have better precision. Okay? And the third method to use is called sample standard deviation. Sample standard deviation is you have a square root of the sample variance. You just have a square root. Okay? Again, if this number standard deviation is smaller, you get data scattering smaller, which is better, right? Which is better. So here I just want to give you an example of the center variance and the scatter data. So this is run, it might be 50 runs, right? And you got an average, x over bar. So this is called arithmetic means. You know how to get arithmetic means, right? Okay, and then after that, if you know the numbers, you know the x for each, each point, numbers of each point, you know the average, right? So you can have standard deviation, sample standard deviation, and you can represent each point like this: x equal to x over bar plus minus n. N is a digital number times standard deviation. So this is what we called error limits. Error limits. Okay? So a typical random variance can be described in this way. So normally, for example, if you have 50 runs and you have average here, normally, if you have standard sample deviation within 3 standard deviations, normally about 99% of the data will be in the range of the 3 standard deviations. And if you have two standard deviation, normally it's about 88% will be in the range of the 2 standard deviation. However, if you have only 1 standard deviation, the percentage will down to two-thirds, which is about 66%, right? So this is the basic, the typical random variables. Okay. So here, this is example is that x equal to 48.2 plus minus 0.6. So this is error limit, right? This is error limit. So that means that x can be in the range of the 48.2 plus 0.6, right? Or 48.2 minus 0.6, in the range of this. But you want to know the mean point is 48.2, right? So, but you want to know what is this error limit. You need to make a definition. It can be a range, right? X maximum minus x minimum. Or it can be 1 standard deviation, or 2 standard deviation, or 3 standard deviation. You need to define 0.6 is 3 standard deviation, or 2 standard deviation, or 1 standard deviation. However, you might have other possibilities, but this is not really. This is normally is not easy to see, or we normally use this. Okay. So make clear what error means. Error limit mean. Okay. Normally, I just told you this. Normally, standard deviation. It can be 1, 2, or 3 standard deviation. Okay. So finally, I want to give you an example of the standard deviation. Okay, this is called quality assurance, QA. So first of all, this is a factory. The factory produces 500 batch per week of the pigment. And then you have a QA quality assurance to control the quality of these 500 batches. So if you do the test and there are some rejection, which is a bad batch, you return. Okay, and if you have if there's others that are regarded as a good pigments, and you can sell it. Okay, so once you have factory, you start to run and to have 500 batch of the pigment every week. And then week 1, you got 17 bad batch. Week 2, you got 27 bad batch. Okay, week 3 until week 12. This is the data you got. Okay, at week 3, at week 13, Y is become 40. Then what happened? The 40 is greater than this, but you want to shut down. You want to continue to work to produce the pigment, or you want to shut down the factories and do the maintenance, or to find out what's going on. So there might be a number you need to follow. The number 40, which this is the number is more than what number can be accepted. Is 40 accepted? As a worker, you might want to ask the manager, why is 40 acceptable? So the manager might tell you that if Y means this one is less than average plus 3 standard deviation, then you can continue to work. The factory will keep on working. Okay, so you need to find out what is the standard deviation of this number. And then if 40 is less than mean number plus 3 standard deviation, you can continue to work. Or if this 40 is greater than standard deviation, mean number plus 3 standard deviation, the factory need to shut down and do the check to find out what's going on and what's wrong with this factory. Okay, so the question of this is, let's find out what's the S here. So why you need to find out Y is which one. So if under the standard deviation, 3 standard deviation. So Y prime if you count this y prime is 19.9, and the standard deviation using this number is 2.8. So once you have 19.9 plus 3 times 2.8, that means what? That means y is equal to 28.3, because there's no bench. The bench is 1, 2, 3. There is no it's an integer number. There's no numbers after decimal point. So 28.3 means the 29. So it depends on the definition. If you run off, that means 28. Okay, so that means it depends on your definition. Okay? In this case, they say 29. So 40 is larger than the 29. That means the 13 weeks, you got 40 bad benches. So you need to shut down the factory. Okay? So 40, you need to shut down the factories. Okay, the question 2 is, if I want a higher standard, that means 29 is too high. I want to reduce the number. I want to reduce from 3 standard deviation to 2 standard deviation. So what is y? So if it's 19.9 plus 2.8 standard deviation, right? That means what? You reduce this is more strict, right? So the y will be 26. That means that if the bench more than 26, the factory need to shut down. Okay, so these are the simple calculation. Please use this for your information. Okay, so the conclusion of the 2.5D will be first, you need to know this is xi, the raw data, the data, all right, the measure data. Range is from the large, highest to the minimum, maximum and minimum. Mean is the average, right? Means the average. Okay, and you need to know the sample variance and sample deviation, standard deviation. And x, each number will equal to the x means plus minus error limit. Okay, so that's it for today. We will talk about 2.6 dimensional homogeneous and the dimensionless quantity in the next lecture.